Hello everybody, and thank you for attending this presentation, which is given by me, Paolo Massioni, and the paper has been co-authored by Laurent Bacot and Gerard Scorletti. Laurent Bacot has written the slide. The title of the paper is Stability of Uncertain Piecewise-Affine System with Parametric Dependence. And we are from Laboratoire Ampère CNRS in France. We belong to INSA Lyon, myself, and other co-author from École Centrale Lyon. Which both formed a part of the University of Lyon in France. So let's go through the content of the presentation. We go first to the definition of the class of dynamical system which we consider. Then we propose some stability results. Then we go through some numerical example and end with some conclusions. So the topic of this paper is the so-called piecewise-affine parameter varying system, which we denote by PWA-PV. They are very close to the classical definition of piecewise-affine system, as you can see, for example, is the famous paper by Johansson and Rantzer, with the difference that here we account for a parametric dependence of the dynamics. So, as in the standard piecewise-affine system, the state space, the space where the vector x belongs to, is partitioned into cells, which we denote by big X of I. And in each of these cells, the dynamics is described by an affine function, as you can see here. The parametric dependence is both in the equation, in the formula here, as well as in the cell as well. So basically the cell can change with respect to a parameter rho, which can change with respect to time. And this is the most general formulation that you can give to a piecewise-affine parameter varying system in our understanding. You might find some previous work in the literature, but they never accounted for variation in the cells themselves, in the partition itself of the state. So as you can see here, more detail of this representation. X is the state, rho is a scalar valued signal, let's say a scalar parameter which will change with time, which belongs to a given interval R. And for what concerns the cell, as we say, you have here the technical details if you wish to read it, but we can just basically point out again that the main feature of this paper we present is that they can change with time. So what is the problem which we consider in this paper? The problem is to find sufficient condition, numerical certificate we can say, of the exponential stability of the piecewise-affine parameter varying system. We have several technical assumptions which we list here. First of all, we assume that rho is bounded and differentiable, and its derivative is bounded by a certain rho d value in modulus. Then the function ai and big and small depend rationally on rho. Also the letters, the symbols ei, big and small, which basically describe the cells, the biggest xi of rho, also depend polynomially on rho. And we also have a last technical hypothesis here, which basically allows the existence of an equilibrium point in the origin. These are rather standard assumptions. This one, basically the dependence polynomially on rho or rationally, which means ration or polynomials on rho, are basically what will allow us to use polynomial methods for dealing with the problem. So let's just take a step back and think of the motivation for these dynamical systems. They can actually be useful to describe nonlinear system with time varying parameters. So as a standard piecewise-affine system can be used to describe nonlinear system, you just take a nonlinear function and approximate with a set of segments. You can do the same in case the system is parameter varying, is time varying. And in general, it's okay to do it for any function, but the problem is that you might need to change also the partition of the function, the place where you cut the different pieces of the state space in order to get an accurate description. And this, for example, is the case of dry friction. You can see here the picture of a dry friction model. Basically, this is the dry friction coefficient as a function of rho, could be the temperature, for example, or a function of the temperature. And basically, rho can change with time according to several factors, and you can see the changing of rho determine the position of the peak, not only the height, not only the height change, but also the position of the peak can change. And so it is natural to look for a description which is piecewise affine, of course, but also which can account for variations in the cells of the piecewise affine system. So, what is the analysis method which we propose for studying the stability of the system? Well, basically Lyapunov analysis. So if you have a dynamical system like here, depending from a parameter rho, and you just need to look for a continuously differentiable function v, kind of Lyapunov function, which is lower and upper bounded by the norm of x, and for which the time derivative of it is smaller than a small number epsilon times the norm of x themselves. Basically, this is Lyapunov definition of a Lyapunov function. And once we have this in mind, then the approach of this paper is just to search numerically for this function v. Once we have parameterized them in a certain way, and just leave the search to a numerical solver. So the first problem, as we say, is the parameterization. There are several possibilities. We choose to do a piecewise parameter varying quadratic function of x, so basically a function which is quadratic in x and depends polynomially in rho. And how to arrive at a solvable problem, a solvable optimization problem, which we like to have convex actually. We can apply basically the linear matrix inequality theory and use as procedure to constrain each piece of this function. We define each piece vi as v defined in each cell xi. We constrain each of these pieces to be a Lyapunov function locally, and of course the function v has to be continuous over all the state space. And in order to use the proper constraints, we need to use what is called the general S procedure, which is the common S procedure for what concerns the LMI formulation, and it is also if you can see if you like, the polynomial version of it, also called the p-sats, for the dependence with respect to rho. We don't go into the details of this because it would make the presentation a little bit too bulky, but of course you can go through it, and in the paper it is described a little bit with more details, let's say. So just to have it very simply put, the first step is parameterization of v. So we need a Lyapunov function which is a quadratic function of x, so it's basically given by a set of pieces. V is depending on a matrix pi bar for each of the cells xi, and pi has this special form over here, so basically it accounts also for the presence of x and a constant 1 in order to account for constants, let's say. So we have to distinguish here between cells for which the origin belongs in it or not. These are the cell I0 for which the origin, which include the origin, and those I which do not include. There is a little bit of difference. It's a bit technical, so I do not go again into the details. And the same partition here is used for the Lyapunov function as for the dynamics, the same partition xy. This is arbitrary. In principle it could be different. This is the standard choice you have in all piecewise-affine papers, if you like. So we choose to do it as well. Then once you have a v chosen, then you can parameterize. This also is the parameterization we propose here. You can look it up here, which basically depends on a matrix T of unknown depending on rho, polynomially depending on rho, up to a certain degree which you can choose arbitrarily, and then depends on this matrix F, which basically describes the borders, the boundaries between the cells. And this parameterization makes sure that the function is constant over the boundaries, same as in Johansson and Ranzer, the seminal paper. And once you have this parameterization over here, then you basically need to look for t after you determine the correct values of f. And once you determine this, then we need to make sure that vi, each piece of vi, behaves locally like a Lyapunov function in each of the cells xi. So it has to be positive definite whenever x belongs to xi of row for each row. And how to impose this? Well, basically you just make sure that vi is positive definite when x belongs to the cell and when rho belongs to the interval. So basically this makes it necessary to add the so-called generalized S procedure terms, which you can see here, this for the cell and this for the belonging to the interval of R of rho. This is a kind of sum of square approach to the problem. So basically this is a matrix which depends on rho, so the positive definiteness of this term is basically checked by checking that this matrix is a matrix sum of square, and to subsequently to check the fact that the time derivative is decreasing, then you have basically to write out the derivative with respect to time, and then again impose this negative definite with respect to the cell and the interval of rho, which makes it again very similar check. You need to check that the matrix with two S procedure or PSATs term is matrix SOS in a given interval. We skip the details, you can read the slides more thoroughly if you like, or read the paper. So you wrapping it all up, when basically the main theorem looks like this. And it is remarkable also that there is no special care to be taken due to the fact that the boundaries are time varying. You can see it here. Basically the time variance will change EI with respect to rho, and also the borders, the boundaries of F of the cells which determine P will also change with respect to time, with respect to rho. But overall you get a series of sum of square checks or matrix SOS checks that you can basically translate into any solver you like, and they become basically a convex optimization problem which can be solved efficiently by your computer. For example, in our paper we use MOSEC, and there is a certain degree of arbitrarity in this transformation from the problem into the convex optimization problem. For example, you can choose the degree of the polynomials. You have more chances to get a solution if you increase the degree of the polynomials, but at the same time you get a more bulky convex optimization problem. And if a solution exists, well, you have the numerical certificate that the system is globally exponentially stable. So now let's go through two simple examples. This first example is a positioning servo system with viscous and dry friction. So as we said in the beginning, if you remember the first slide, there was a curve of the dry friction. We assume that there is a mass moving under the effect of some actuator providing a force, and in feedback loop you have a control loop, but you have this dry friction over here with that shape. And so it is a relevant question in many mechanical applications, mechanical systems, to see if the system is stable. And with this description, basically we can answer this question with a numerical procedure. So without going again into the details of the expression, you can basically write out the function in this way, the function that you've seen in the picture before, the model of the dry friction, and then this is basically originates a piecewise-affine function, a piecewise-affine system depending from rho, which rho can be related to the temperature and can change with respect to time, not arbitrarily fast, but it can change. So once you have taken this we have written this model down, then you can derive basically the cells. There are 5 cells. Basically one is the cell for the slow movements near the origin, say near the equilibrium, and then you have 2 cells on each side of the say the velocity, 2 for positive velocity and other 2 for negative velocity. And the search of the Lyapunov function can be done only on the positive side, and the other part will be just given by symmetry. And then basically, if you're interested in the details, you can work out all the matrices A1, A2, A3 bar, and also the boundaries. And you can see the boundaries depend on rho. The cells, let's say the cells depend on rho. As we said, the peak of the coefficient is determined by rho, and so if rho moves, you have to move the place where you split the function into, so you have to change basically the position, the definition of the cells. So to make a long story short, you can try it out and put into MATLAB and solve it with Mosaic as a matrix sum of square problem, and with degree 3 of the degree 2 for the Lyapunov function, you get basically this result. You see, it depends on rho square, which gives you a successful solution for the problem, and then you basically prove that the servo system is globally exponentially stable, even if rho changes, provided that it changes not so fast, according to the constraint given here. Second example, classical example from the literature, from the paper of Johansson and Ranzer, we call it the flower, or the four-leaf flower if you like. We see it wide, it's in the paper from '98. We just add a little bit of variation. We add the rho dependency on the cells, and then you can prove basically that this system is exponentially stable for a given value of the parameter. Why we call it the four-leaf flower? Because if you draw the level curves of the Lyapunov function, you basically see some four lobes appearing. It looks like a flower with four petals or a four-leaf flower. So let's conclude. This work basically provides a very general framework for piecewise-affine system depending on a parameter, a scalar parameter, but you can think of extending to several parameters. And the main novelty of this paper is the dependence of the partition itself. And of course, for future research, you could have a multivariate parameter dependence, as we said, and you can also go through performance characterization, not only, for example, stability, but also, for example, L2 gain, to think about it, or even more fancy kind of performance. So that's all. Thank you very much for listening. And if you're interested in the paper, just contact us, please.